Okay. Welcome everybody to our third webinar with our grantees. This is Dr. Andrew Thaler. He's here to talk to us about robots. Thanks for joining us, Andrew.
Sure thing. Thanks for having me.
Andrew is going to talk to us about flying and swimming robots, more precisely drones and ROVs. Andrew is one of our 2015 Ocean First Education grantees, and he's been working on developing new tech for marine conservation using drones and ROVs. And he's also spent a lot of time training a young and up-and-coming marine scientists in high school and college how to use and get trained in these tools and building skills up so they can kind of have a step forward into this world and be up to date with marine conservation strategies. Now, before I hand it over to Andrew, I want to remind everyone, Thursday we'll be having a Twitter chat with Andrew again at Southern Fried Scientist. We will be talking about pretty much what we're talking about today, and it's a chance for you to sign in and get some questions answered by him personally. We'll have a question and a session after this, and but on Thursday you can catch him again. So, and lastly, I want to remind everybody that we have our social media presence at Ocean First Education. So be sure to get on Twitter, Facebook, and Instagram for those, and follow us on all our great content. So Andrew, let me hand it over to you, and I'm going to mute out of this so you don't hear me breathing, and take it away.
All right, great, thank you. And just for a little clarification for the Twitter chat on Thursday, I have a second account that's at sfriedscience. Is a bot that only tweets marine conservation news. So sometimes people will try to get in conversations with the bot because my actual Twitter handle is at sfriedscientist. So if you're looking for that and you don't see any responses, you might be talking to the robot with the very similar name to me. I do robots for a lot of things, and let me cue up my screen share and start talking about that. So I am a deep sea ecologist by training. The environmental impact of anthropogenic actions on hydrothermal vents, primarily in the Western Pacific, and primarily surrounding this emerging industry of deep sea mining. So I'm not going to get too much into that, except to say that the vast majority of my career has involved working with very, very large robots. Like this is the ROV ISIS that is used by the British Research Institutes. It's based out of National Oceanographic Center in Southampton. And we use this to explore the Mid-Cayman Spreading Center in the Caribbean Ocean, about 80 miles south of the Cayman Islands. Actually, the same trench that The Abyss, the movie, was set in. So that was really fun. But these robots are expensive. They're very, very technical to operate. They're very, very expensive to operate. They need a support team of 5 or 6 people in addition to the science team. The robot itself costs about $4 million. Every day on the boat costs close to $200,000, sometimes even more. And there's very few of these in the world, and access to them is pretty restrictive. You have to apply for a grant. You have to get funding to go out and use them. So they're really, really powerful tools to do marine science exploration, but they're really bad at being used to engage the public. So a lot of what I do is marine conservation outreach. I run a website, Southern Fried Science, which is, depending on the month, either the most visited or the second most visited marine science and conservation website in the English language. And so I really wanted to find tools that could first be used for outreach, to help people connect with the ocean, to help people learn about the ocean, to help people explore the ocean. And as I kind of progressed down this train of thought, I also realized that citizen science is an incredibly powerful tool for mobilizing communities, for educating people about the ocean, and for generating real and valuable data about the state of our oceans. So I, in addition to looking at smaller robots for outreach tools, began exploring them really as research platforms, powerful research platforms. And the group I ended up finding was a team of guys out of Berkeley, California. I'm based in Virginia now. I was based in North Carolina at this time. But I found this group in California called OpenROV, and these guys were really trying to develop, they're technology geeks. They wanted to develop an open source underwater robot because they enjoy the challenge of figuring out how to do something like this cheaply. And they're explorers. They wanted to look at, they wanted to get people connected to the ocean. They wanted to give people tools to explore, and they wanted to develop the technology to enable this. And so I partnered with these guys at OpenROV to really begin exploring the potential for this particular robotic platform as a tool, not just for exploration, not just for outreach, not just for playing in the ocean, but also for doing real science. And so just to give you a little bit of an idea of what these robots can do, they're small. You can sort of get a sense for how big they are. They're about the size of a shoebox, though I've been told now it's more accurate to say a blue apron box. That apparently provides better context for people. They're not huge. They're very, very portable. You can carry them around the world. You carry them on your carry-on luggage on an airplane. I actually can have a case that fits underneath the seat in front of me on an aircraft. So they're really, really portable. They're easy to use. They're inexpensive. These are about $900 a piece. Well, all told, when you add in all the other components and everything, they cost about $1,300 to $1,500. And they come as kits, which is really valuable for two reasons. Because it's a kit, it's also a STEM and STEAM learning experience. So you can use them as teaching tools to teach kids about robotics, to teach kids about programming, to teach kids, and I say kids, you know, kids from 9 to 99 kind of setup. So, you know, they're really powerful tools for education. It comes with pretty good instructions. So, I'm sorry, I'm getting a lot of feedback. Can someone turn off their microphone? So these are really, really great educational tools in terms of training people about robotics, but also in terms of teaching people about marine ecology. Because what we did first with OpenROV, our big push was to design this program. This is what these pictures are for. This is actually figure 1 from my last paper on OpenROV, which was an exploration of using robots to study invasive species and mitigate transmission of invasive species via ultra-portable research platforms. So we designed this course out in Papua New Guinea with a bunch of colleagues of mine from the University of Papua New Guinea. And we went out to a remote field station called Nago Island Fishery Station in Keviang, which is about as far away as you can get without being totally cut off from technology. So we were very, very remote. It took about 3 days to get to the field station. And we flew out there with 6 kits, so completely unassembled robots. And over the course of 3 weeks, we had 23 advanced undergraduates from the University of Papua New Guinea basically build these robots from scratch. And while they were building it, they were also designing the research projects that they would be conducting with the robots for the last week of the course. And so this all sort of came together in this, the overarching theme of marine ecology via remote observation, where not only were we teaching them how to be marine ecologists conducting fieldwork using the robots, but we were also trying to teach them how to be robotics technicians as well, so that by the end of the course, they were fully fluent in how the robots worked. They could repair the robots on their own. They could fix them. They could modify them. One of the big advantages of this particular platform is that it's very hackable, so you can add a lot of new systems to it. And they also had a little bit of training in marine. I mean, it's a 3-week course. You can't really create a marine ecologist in 3 weeks, but we gave them a really strong introduction to it. And because of the way that the university system was set up in Papua New Guinea, for most of these students, this was their first real chance to be out in the field. And these were sophomores, juniors, and seniors in the marine and environmental science program. So this was really their first field opportunity to go out and really do their own kinds of studies. And from that, we ended up publishing 1 paper, and there's been a bunch of other ongoing studies. The 6 robots they built were then donated to the University of Papua New Guinea, so they're still out there as permanent robotic assets for the university to use. And the last time I checked, and this was about 3 months ago, 3 of the robots were out being used to do coral reef surveys somewhere back in New Ireland, which is another one of the Long Island chains in Papua New Guinea. So that's kind of the more formal education that we can do with these robots, but there's a lot of informal education that we can do with these robots. So this is a Bioblitz that we hosted in Lake Merritt in Oakland. And the purposes of Bioblitz is you bring a bunch of people from the community together, and you pair them up with naturalists, and you go through a designated, a specific discrete region, and you survey all the wildlife you can find, all the flora, all the fauna, anything, and you kind of do this kind of a blitz of natural science where you kind of get a really, really good overview of the biodiversity of a specific region. Lake Merritt is interesting because it's a tidal lake in the middle of the city of Oakland. So there's a lot of really fascinating biology happening in it. It's sometimes during the day it's fresh, sometimes during the day it's salty. It's got a sea gate, so they can actually control the tidal flow of it, and that has very interesting implications for how that affects the communities that settle within Lake Merritt. But Oakland is a fairly large city with a fairly notorious reputation, and you can't swim in Lake Merritt, you can't snorkel in Lake Merritt, you can't survey Lake Merritt with scuba divers because no one really wants to get in the water. It's hazardous, and so that's the kind of environment where robots really thrive. They're really ideal for those kinds of things because where a person couldn't go, say a sewage outfall or the hot water vent of a nuclear power plant, which we have some friends out in Florida that are using ROVs to survey nuclear power plant outfalls, you can send robots in, and you don't have to worry about safety, and you don't have to worry about the health of your divers. So you can put them into much, much more hazardous conditions. And when it's a $900 robot, it sounds like a lot for a citizen science program or for a personal robot, but in terms of when you compare to the larger research robots, I know there are some groups that almost treat these as disposable for certain activities because it is relatively inexpensive compared to just about anything you can do, even compared to sending in a dive team. You know, sending in a team of Navy or Coast Guard divers to investigate something costs way more than $900 for a day of diving. So they work really well for the kind of higher level undergraduate, graduate student STEM education. They work really well for these kinds of citizen outreach projects, and they work really well. I'm sorry, this slide is out of order. I'm going to go to the next one. And they work really well for high school science programs. So this is one of the workshops that Ocean First Education funded through the early career fellows grant that I got. Thank you, Caine. And this is with the Gloucester RoboDukes. These are high school students from our local high school. My local high school actually has a robotics team. They do things like VEX and Sea Perch and Mate. And so I got together with the coach of the robotics team there, and we brought 8 of the students out to the Virginia Institute of Marine Science for a long weekend where they got to build 2 of these robots. And along the way, they got to meet some of the marine scientists at the Virginia Institute of Marine Science. They got to interact with people. They got to take the robots out and dive in the York River, which is, you know, not the most fascinating body of water to send a robot into. The visibility is not fantastic, but there's certainly a lot of interesting things there, and they got a chance to be ROV pilots for a day. And then they got to keep one of the robots. So one of the robots went back with them to the Gloucester high school for them to continue developing on and hacking on and playing with and learning new things to do with it and using it for their other robotics competitions. And one of them stayed with VIMS, and we use that here to do coastal surveys here. And we're slowly putting together plans to start doing oyster reef surveys using these small robots, and particularly water quality sampling and other systems like that. So the robot itself has become a very, very useful asset, both for the high school, which can now use it as a little bit of a learning experience for them. It's very important for things like Sea Perch and Mate, for those who don't know, are high school and university robotics competitions hosted by NOAA, Office of Naval Research, and the Woods Hole Oceanographic Institute. That's designed to have the students design robots from scratch and use them and operate them, and they have a series of tasks they can do. I think this year the tasks were all based off of a mission to Europa, so what you would need to do to pilot a robot on Europa, which is cool because it has a lot of sort of remote telemetry and telepresence systems and all this other cool stuff about how would you design that. But having an actual completed robot that you can, that's used professionally and used commercially, that they can then get some experience on to understand what are the limitations of these robots, what do they really need to design around before they start, can be very, very valuable for these kinds of programs and very helpful for students who want to continue on with their robotics education. So I'm going to sort of segue from the ROV into the drone, the UAS. I'm sorry, lots of acronyms. ROV is remotely operated vehicle. It's what we generally used to refer to as underwater robots. UAS is a uncrewed aerial system, so it's a drone, it's a quadcopter, it's a flyer. But kind of to lead this transition, I want to talk about another program I have going on called Oceanography for Everyone. And Oceanography for Everyone really captures that citizen science ideal for operating these kinds of programs. What Oceanography for Everyone does is it is sort of an extension of what OpenROV started and what I started with a few other programs, but it's designed to develop tools for citizen oceanographers, so real oceanographic tools that can be built cheaply and used to produce high-quality scientific data. So we use a lot of 3D printing, we use a lot of fabrication, we use a lot of electronics. This is actually my workbench on the in the dry lab of the RV Blue Heron, which is a research vessel based in Lake Superior. And what I was doing here was doing a field test for the rapid prototyping of research materials at sea. So the idea was that I would come on board with very few actual oceanographic tools with me, but with a 3D printer and an electronics fabrication lab. And during the course of the cruise, we wanted to see if we could actually fabricate all the tools that we would need to conduct the research that we were proposing. There's a tube in the back with a red cap on it. That's a CTD. A CTD measures conductivity, temperature, and depth. It's what you use to do a water column profile. You can't really see it because it's sort of attached to the robot, but there's a Niskin bottle that's almost entirely 3D printed. Niskin bottles are used to take discrete water samples. So the idea is that, obviously, you know, if you plan a real research cruise, you bring the tools you need with you, of course, but the idea is, like, you know, when you're out on a 30-day deployment, when you're out on a 60-day cruise and something breaks, you're kind of out of luck unless you can refabricate those tools. And by sort of developing these systems where you can create them as you need them, it fills that need. And it also fills that need very cheaply. So the other idea with Oceanography for Everyone is that anyone can become an oceanographer. We have on our website instructions for how to build all of these tools, instructions for how to use them, all the software needed. It's all open source, so anyone is free to download and modify and use as they will. And we have the basic tools that you would need to conduct oceanography. We have a CTD, we have the Niskin bottle, which is the water sampler, and we also have a field laptop, which can be built for like $200. I think a little less now. Depends on the ebb and flow of cheap electronics coming out of Shenzhen. But we've generally tried to make these very, very affordable packages. And when you compare them to the actual commercial system, so we put our CTD up against a commercial CTD on the boat. The commercial CTD costs $60,000. Our CTD costs $140. You couldn't tell the difference between the data coming out of the two systems. They were basically indistinguishable in terms of accuracy. The more expensive one had a higher sampling rate, so I mean, there's always trade-offs. You get you know, a couple of thousand samples every minute versus a couple of hundred samples every minute. But those are things you can control for and adapt to. And the idea is that we want oceanography to be as accessible to as many people as possible. Anyone interested in learning about their own waterways can build their own tools, can go out and survey. Fisherman wants to know something about his fishing grounds, he can build his own equipment and go out there. And then we, of course, provide support and education and anything else that people would need. I'm going to now jump ahead to the final piece of this puzzle, which is the eco-drone. And this is a big, big component of the early career fellowship that I got from Ocean First Education, was building this marine ecology drone. This is the ultimate marine eco-drone. And unfortunately, we don't have a lot of pictures of this thing in action because developing new experimental aircraft is a slow process with lots and lots of work and modification and unexpected unplanned events. So the way this drone works is it's a standard quadcopter. It's fully autonomous. One of the big things you want to think about when you're building big autonomous systems, and you can see in this picture, it's not a small drone. If you're familiar with the little DJI Phantoms that a lot of people use, those little white drones that you see everywhere, each propeller of this drone is longer than a DJI Phantom. So it's a pretty sizable machine. It's a flying lawnmower. You have to be very, very concerned about safety, about public safety, about not interfering with airspace when you're flying something this big. So, and one of the biggest problems with drones is that they have pilots for the most part. When you've got someone, the pilot is almost always the source of the error when you have these systems flying. So the idea is to get the pilot as much out of the system as possible. You still have the ability to take control of it in emergency, and really the only thing you ever want to do when you're flying one of these is land it. You don't really want to try to take control and maneuver around things because the onboard computer is better at it than we are. But the idea behind this drone is that it can do water-based takeoff and landing. It's sealed against the environment, so it can fly in rain, it can fly in heavy wind, it can take a pretty sizable beating. It's equipped with a really high-resolution camera, so from 400 meters up when we're flying, or 400 feet up, which is the FAA limit for these small quadcopters, we can take a sub-centimeter resolution of, say, coastal erosion. We can track things like a harmful algal bloom. And then eventually, this will have a water sampling payload, so it can actually do things like detect a harmful algal bloom, land on the water, take a water sample, and then return to base with the water sample so that we can then do downstream analysis of the water sample. We can determine what species of algae is causing the bloom. We can do some population genetics analysis of these things. We can look at the biodiversity of blooms. We can look at the movement of blooms over time. Currently in the York River and the Chesapeake Bay, there are usually only 2 or 3 harmful algal bloom aerial surveys every season. So getting a plane up there to do these surveys is very expensive. Having a drone platform like this would allow us to do the surveys almost in real time. We could do a flight every day and really track the movement of these harmful algal blooms over very, very short time scales, which is really useful for the ecologist studying this. It's really useful for human health. It's really useful for understanding how these blooms are altering ecosystems on a daily basis. So that's what this is that's what this whole system is for. We have a couple other programs going on. We're taking you out to North Carolina later this summer to do shark surveys. So we want to determine if we can identify sharks to species via aerial surveys. We'll be doing that in conjunction with some work with OpenROV, so that we'll have underwater robots and aerial robots operating simultaneously. Unfortunately, because it's an experimental aircraft, we still run into some problems. So right now it's back with the manufacturer, who's a very good buddy of mine, who's one of the finest drone builders probably in the country right now. He builds very, very tough equipment. But no one's really ever built a drone that can do water-based operations the way we want to do it. So we had some problems with the servos getting corroded, and so it's back in the shop getting some upgrades. But hopefully before the summer season begins, we'll be back in the air and flying and putting this thing through its first season of field trials. So that is my general spiel, and I think we have time for questions was the plan, and I'll be happy to take any questions and talk to you about any of these programs.
Hey, Andrew, that was awesome. Really interesting to see how far drones have come and where you're taking them as well. I see lots of potential in the marine conservation science world for that drone. Let's open up to questions from everybody. I have a quick question. Well, I have a couple of questions to kick it off. What's the payload of that thing?
20 kilograms.
Well, that's quite a lot.
And so it's 20 kilograms, but that is not including batteries, so it's a trade-off. The batteries are heavy, and batteries give you air time, so you can do a really short flight and haul something very heavy, or you can do a really long flight and haul something pretty light. So You know, it's the same equation you have with NASA with a rocket, and how much fuel can you put in because you have to take the fuel up with you and all that. But the advantage of this is that the batteries get lighter and lighter and lighter every year, and so you know, the aircraft keeps improving just based on battery tech going up.
Yeah, I mean, I see. You know, I don't know how heavy a LiDAR is, but if the LiDAR's ever got light enough, that would be great for coral reef surveys. I know we use that a lot. You still there, mate?
Yeah, I'm right here.
Oh, great. I had a little look out there. So shark surveys, tell me about those. How do you plan on kind of ground truthing the aerial images of you know, the top side of a shark?
So in North Carolina, there's a few it's pretty well known which species are there. We're going to go to very high populated areas. And we're partnering with some guys out of ECU, so there will also be kind of more formal surveys where they're going out and catching sharks as well. You know, it's experimental at this point, so we're going to try a lot of different angles to make sure that we're getting the ideas right. For things like hammerheads, we're pretty confident we can identify a hammerhead versus a bull shark. For things like the difference between a bull shark and a lemon shark, I'm not entirely sure yet. I'm not the shark expert, so our shark guy is the one who I trust has the ability to make sure the IDs are positive. And the other thing is with that survey, we're partnering with some local townships. So in addition to doing it as a biodiversity survey, also as beach monitoring as well. So less concerned about the identity, more concerned about presence for some of that kind of thing.
Yeah, indeed. And also probably a fair bit of interest from local councils perhaps in having a drone that can be waterproof, used for aerial survey to keep swimmers potentially more safe.
Yeah. All right, I see a couple questions in the comments. Why can't you put a waterproof case around the drones to prevent water coming inside? You can. It's sort of what we've done. We have a lot of drones have an airframe that's kind of exposed, so a lot of the electronics sit on the outside. Ours, if you saw from the picture, is completely enclosed, and then it has flotation underneath, and the camera is in a waterproof housing. All of that adds weight, which is one of the big issues, so you have to design around that added weight, and you have to design around the added size. And all that affects flight characteristics. So one of the big problems we have is that, you know, water has friction, water produces surface tension. So you really have to be careful about how you design the drone so that when it takes off from the water is going to pull it back down, and it's going to pull it down in ways that could affect its flight. And in a lot of the early tests with some of the earlier water drones that we've built, the drones actually end up flipping over and going right into the water. These drones can survive a little bit in the water. Caine has a story about one that went for a swim and came back just fine. It's really the long-term exposure that's more of the issue. We have a question. Have you ever helped an elementary class make an ROV? I haven't personally. I have a colleague that runs, they're called Girls Underwater Robot Camps. They're based out of Berkeley, California. And I think she's done courses with students as young as 12 and 13 is the youngest she's gone. I haven't had building classes with younger people, but we've done ROV piloting classes with students as young as, well, the youngest pilot to ever fly one of the open ROVs was 2. So you can definitely fly them when you're pretty young. They're actually controlled via a video game controller. So what we discovered a lot of times is that the younger kids are much, much better pilots than any of us are because they're much more intuitive with these controllers. When I started working with OpenROV, it was the first time I had picked up a PlayStation controller in about 10 years, so it took a while to get used to all the joysticks and stuff. The big commercial ROVs have very, very different control structures, and they're much, much less responsive as well. The range of the drone is, again, one of those things where it depends on the battery life. Right now, the FAA has some pretty tight regulations about the use of drones, so you're not actually allowed to fly beyond line of sight. So the range of the drone is significantly greater than line of sight for our purposes, and so we really haven't pushed it all the way as far as you can go. Our flight time is, when fully loaded with batteries, you get about 45 minutes of flight time, and it can fly up to about 15 or 18 miles per hour, so you can get pretty far away in a 40-minute flight. Anyone else with questions? Did I lose the feed? I'm not hearing any sound.
Andrew, can you hear me?
Yes, I can hear you.
Oh, great. I have one question about illegal fishing.
Okay.
By anyone about using it for aerial surveys of illegal fishing in other parts of the world?
I haven't. I know some colleagues that have. The big problem with that is that quadcopters aren't the best platform for that. What you want is a fixed-wing drone for things like that because they have a much, much greater range. They don't have the precision control that you get with a quadcopter, and you certainly can't do things like vertical takeoff and landings. But they can, I mean, the military drones are fixed-wing drones, and they can fly for as long as you can keep them in the air. They're gas-powered, so they stay up much, much longer. I also, I have worked a little bit with people out of the Cherry Point Air Station in North Carolina. So the military drone guys are very keen to help the marine conservation community with aerial surveys because they have requirements for flight time. They have to fly X number of hours for training every month to stay recent in their certifications, and they'd much rather be doing something useful with those flight times than just flying around in circles. And so we've been able to get some volunteers from the Cherry Point Air Station to go out and do coastal mapping with some of the big military drones as well.
Excellent. Yeah, I mean, there's some parts of the world where there's dynamite fishing and things. I wonder if even just the presence of just a drone in the sky would reduce the impact. Even if it wasn't filming or carrying a huge payload to do anything, just flying it up and down the beach might be enough to deter people from using dynamite to blow up coral reefs. So an interesting avenue also.
Yeah, and those kinds of things are coming down. I know there's some groups that are planning to use them to monitor marine protected areas. So one of my favorite proposals I've seen. It hasn't come anywhere close to reality yet, but it's definitely something. It's one of those pie in the sky things that people really want to do. Is put up a network of hydrophones along the edges of where the marine protected area barriers start, and when the hydrophones detect a boat motor, a little drone is launched autonomously to zoom out to triangulate the location and just take a look, make sure they're not fishing, and then fly back home.
Seems cheaper just have a guy in a boat out there watching what's going on.
Yeah. Well, and because it's autonomous, it can respond whenever it needs to. There is a real project in the Amazon that uses old cell phones as microphones. So there's a little array of cell phones throughout the jungle that can, there's enough of them that they can triangulate positions based on sound, and they're looking for illegal logging. And so when the microphones pick up chainsaws, they triangulate the location, and they're still using live pilots, but they'll send a little quadcopter out to see what's happening there and record it. And they've caught a few people doing that already.
I love it. Klara has a question. Where do you see your research going in the future, and what's your ultimate goal, I guess?
So I am, you know, I'm very excited and very enthused about all this technology, but I also have a little bit of a reputation as the wet blanket in the marine technology world. A lot of my research is involved in figuring out how these tools can be used, but also figuring out how these tools can be used in such a way that they don't cause other unintended consequences. So my last big research project with OpenROV was looking at their potential to act as invasive species vectors and developing a set of guidelines to sort of mitigate that. So best practices for ROV users so that they don't accidentally transport invasive species with their robots. And this came about because we were out in Papua New Guinea and we were kind of giving sort of our experience spiel, and one of my colleagues was talking about her ROV that she had built in Greenland. This is the one who runs the Girls Underwater Robot Camps, and she had done a camp in Greenland with a First Nation community. So she had a bunch of young women from this First Nation community build this robot, and then it had dove in Greenland, and then it went across to Newfoundland, and then it came down to Cuba, and she spent a couple of weeks doing research in Cuba, and then it came across to San Francisco, and spent a couple of weeks working in San Francisco. It went up to Lake Tahoe, which is a freshwater lake in the mountains, and then it went to Papua New Guinea. And I'm hearing this story, and of course it's an awesome story, and it's great to hear, and these things are amazing, and they're portable, and that makes exploration and research really, really accessible. But I'm hearing this being like, oh my God, what if you had picked up, a couple of limpets from Greenland and released them in Papua New Guinea, and we come back and the ocean floor is just covered in these things. So we sat down and we spent a couple of months really fleshing out what the proper protocols would be to make sure that these robots aren't accidentally or unintentionally transporting these kinds of invasive species. I've done some work looking at the impact of drone systems on whales. So are whales bothered by drones? Are they more bothered by drones than they are by, say, a boat? They're not. Depending on the drone, they're usually not. I'm really interested in getting these technologies out there, and I'm also really interested in getting the technology out there safely, because of course it just takes one incident and everything's locked down, and you're in a situation like we are with the National Park Service, where you just cannot fly a drone in national park airspace because too many people have been reckless about them and dropped them in the ocean, dropped them in hot springs and done some damage in the parks. I think there was a video a while ago of someone chasing a bighorn sheep with a drone, which was just not great. So figuring out how these systems can be used safely while simultaneously getting them into the hands of as many people as possible, because these really are incredibly powerful tools for conservation, for monitoring, and for research as well.
Yeah, I agree. You're doing a great job, and it's awesome to see someone taking the initiative to kind of make them salt waterproof and to be able to expand that realm, because we have a lot of ocean to monitor and protect and understand, and these tools are definitely advancing that at a rapid rate. So thank you for all the work you do. I think we'll leave it there since we're at the end of the questions. Thank you, Andrew, for your great work. We hope your drone comes back with the repair that's needed to get you in the sky again. And we look forward to watching that on Twitter and following your work. So remember, everybody, Thursday at 10 a.m. Mountain Time, we have a Twitter chat again with Andrew, and he's there to answer some more questions that you may have. And thank you, Andrea. Yes, you always tune in. Thanks again for having your classroom here. And we'll see you on Twitter on Thursday, Andrew, and good luck with the rest of your work.
All right, great. And thank you all for joining in.
All right, thank you.